The prediction nobody wanted to test. The math was clear, the logic was sound, and everyone hoped it was wrong. This prediction did not come from an experiment or an observation. It emerged quietly from equations, sitting there like an accusation. If the theory was correct, then reality would behave in a way that felt deeply uncomfortable. So uncomfortable that many physicists wished the prediction would simply remain untested. The prediction arose from quantum mechanics, a theory that had proven extraordinarily successful, yet contained implications that challenged fundamental intuitions about how the world operates. This particular consequence suggested that particles separated by vast distances could exhibit correlations that defied classical explanation, a phenomenon that would later be called entanglement. To understand why this matters today, we need to look at how science usually progresses. Predictions are exciting. They point toward discovery. They promise confirmation. Most are designed to be tested, celebrated, and absorbed into knowledge. Scientists typically embrace predictions because they offer opportunities to validate theories and expand understanding. A successful prediction confirms that we grasp nature's workings. It builds confidence and opens new avenues for exploration. Testing predictions is what science does, but this one was different. Testing it meant risking the foundations of what people believe reality to be. It implied effects that defied intuition, outcomes that challenged causality, results that would force a rewrite of how the universe was interpreted. The prediction suggested that measuring one particle could instantly determine properties of another particle arbitrarily far away, despite no signal passing between them. This violated the deeply held principle of locality, the idea that objects are only influenced by their immediate surroundings, and that influences propagate at finite speeds. At first, the prediction was treated cautiously, a theoretical artifact, something that might disappear once the math was refined. But every attempt to remove it failed. The logic tightened. The conclusion remained. Physicists scrutinized the derivation from every angle, searching for mathematical errors or hidden assumptions that could be relaxed. They hoped the prediction was an artifact of idealized models that would vanish when realistic complications were included. But the more carefully they examined the mathematics, the more robust the prediction appeared. The deeper physicists dug, the more disturbing the implication became. If this prediction was correct, then nature allowed behavior that no one was ready to explain. The universe would be stranger, less intuitive, and far less forgiving than expected. The correlations predicted by quantum mechanics could not be explained by any model where particles carried predetermined properties or where influences propagated locally. Either particles were connected in ways that transcended space, or the very concept of independent reality needed revision. Neither option was comfortable. For a long time, the prediction stayed safely on paper, untested, unconfirmed, not because it lacked importance, but because confirming it would change too much. The prediction challenged Einstein's principle of locality, an intuitive notion that the universe operates through local cause and effect. Testing it would require creating and measuring quantum states with extraordinary precision, technology that did not exist for decades. Many physicists were content to treat the prediction as a philosophical curiosity rather than an empirical question demanding resolution. Eventually, technology caught up. Instruments became precise enough. Conditions could finally be created, and the question could no longer be avoided. Advances in laser technology, photon detection, and quantum state preparation made it possible to generate entangled particles and measure their properties with sufficient accuracy. The theoretical prediction could finally be subjected to experimental scrutiny. The moment of reckoning approached. What nobody wanted to test was about to step out of theory and into reality. And once it did, there would be no going back. The experiment would either reveal that quantum mechanics was incomplete, vindicating those who found its predictions unacceptable, or would confirm that nature operates in ways that fundamentally challenge classical intuitions about reality. At first, physicists searched for loopholes. Maybe the prediction relied on an idealization. Maybe real systems would hide the effect behind noise or complexity. Reality, after all, often softened the sharp edges of theory. Scientists proposed that perhaps hidden communication between particles could explain the correlations, or that measurement settings were somehow predetermined in ways that mimic quantum predictions. These loopholes offer potential escape routes from the disturbing implications, ways the universe might preserve locality despite appearing to violate it. But as experimental designs improved, those hopes faded. The conditions required were extreme, but not impossible, and the prediction remained stubbornly intact. If the theory was right, the effect had to exist. Experiments were designed to close each loophole systematically. Particles were separated by distances that light could not traverse in the time available for measurement. Detection efficiencies were improved to eliminate sampling bias. Random number generators controlled measurement settings to prevent hidden correlations. One by one, the escape routes were sealed. This created a growing tension. Testing the prediction meant trusting mathematics over intuition. It meant accepting that reality might behave in ways that felt almost pathological. Outcomes could depend on arrangements that seemed meaningless. Cause and effect could blur at the edges. The predictions of quantum mechanics demanded that measurement results at one location instantaneously influence the statistics of measurements at distant locations, despite no causal signal connecting them. This spooky action at a distance, as Einstein dismissively called it, seemed to violate everything physics had learned about how influences propagate through space. As proposals circulated, resistance grew, not political, but emotional. Some predictions are dangerous because of what they imply. This one threatened the idea that the universe was fundamentally well-behaved, that beneath complexity lay comfort. Many physicists had built their careers on classical intuitions about locality and realism, the idea that objects possessed definite properties independent of observation. Confirming quantum entanglement would undermine these foundations, forcing a reconception of physical reality that felt almost metaphysical in its strangeness. Eventually, the first tests were run. Carefully, cautiously, the setup was refined to remove every alternative explanation. Controls were added. Variables were isolated. The universe was given every chance to behave normally. Experimentalists created pairs of entangled photons and sent them to distant detectors. They measured properties like polarization and compared the results. They varied measurement angles systematically. They collected vast amounts of data to achieve statistical significance. It didn't. The results matched the prediction with unsettling precision. Subtle at first, then undeniable. Reality was doing exactly what the equations said it would do, no matter how much it conflicted with expectation. The correlations between distant measurements exceeded the bounds that any local theory could produce. The violations of Bell's inequality were clear and reproducible. Nature was exhibiting coordination that could not be explained by hidden variables or local interactions. Quantum entanglement was real. What had been feared as a theoretical oddity was now evidence. The prediction nobody wanted to test was no longer hypothetical. It was real. The experiments confirmed that particles separated by kilometers exhibited correlations that violated classical limits. The universe genuinely allowed connections that transcended spatial separation, connections that could not be attributed to signals or hidden communication. The foundations of classical physics, locality and realism, could not both be maintained. And with that confirmation, the conflict shifted. The question was no longer whether the prediction was true. It was what it meant for everything else we thought we understood. If quantum entanglement was genuine, then either reality was fundamentally non-local or it lacked the kind of objective definiteness that classical physics assumed. Either conclusion demanded a profound reconceptualization of physical theory. The conflict deepened as the implications were traced outward. The confirmed prediction did not stay isolated. It touched other principles, pulled on assumptions, and loosened ideas that once felt secure. What seemed like a narrow result began to ripple through physics. Entanglement affected how information was understood, how measurement worked, how quantum systems evolved. It touched foundational concepts like causality, determinism, and the nature of physical properties. At the heart of the tension was causality. The prediction allowed correlations that could not be explained by local causes. Outcomes were linked without any signal passing between them. Distance stopped acting like protection. Separation no longer guaranteed independence. When one particle was measured, the outcome was correlated with measurements on its distant partner in ways that could not be attributed to any mechanism involving signals propagating between them. The universe somehow coordinated results across space without any identifiable causal connection. This build-up forced an uncomfortable choice. Either reality allowed influence without communication, or the concept of influence itself needed revision. Both options felt unacceptable by classical standards, yet the data allowed no third path. If influence required signals, then entanglement should not exist. If entanglement existed, then something about our understanding of cause and effect needed adjustment. The universe was presenting a stark dilemma that could not be resolved within classical frameworks. Attempts to soften the conclusion failed. No hidden timing, no delayed effects, no overlooked interactions. The correlations were real, measurable, and immune to explanation within older frameworks. The universe was coordinating outcomes in a way that ignored intuitive boundaries. Every attempt to find a loophole or alternative explanation encountered obstacles. The data consistently confirmed quantum predictions and violated classical expectations. Nature was unambiguous in its verdict. Emotionally, this was destabilizing. Physics had always relied on locality. Things affected nearby things. Causes spread outward at finite speeds. Now, the universe was demonstrating connections that defied that narrative without breaking any measurable rule. Entanglement did not allow faster-than-light communication or violation of relativity's speed limit, yet it created correlations that seemed to require instantaneous coordination. This tension between quantum mechanics and relativity remained conceptually troubling even as both theories continued to work perfectly in their domains. By this point, the prediction had done its damage. It had not violated physics. It had violated expectation. The universe was obeying its laws perfectly, while quietly revealing that those laws allowed behavior humans were never meant to find comfortable. The mathematics worked. The experiments agreed. But the implications remained deeply counterintuitive, challenging cherished notions about how reality operates. The remaining question was no longer about acceptance. It was about consequence. If this behavior was real, then the structure of reality itself was more connected, more constrained, and more subtle than anyone had imagined. Entanglement revealed that quantum systems could not be understood as collections of independent parts, each with its own definite properties. Instead, they formed holistic wholes where the properties of parts were fundamentally interconnected. The climax of this story is not shock, but resignation. The prediction nobody wanted to test was not an anomaly. It was a window into how nature actually operates beneath the classical approximations that govern everyday experience. Once confirmed, physics did not collapse. It adjusted. The universe had not broken causality. It had exposed a deeper structure beneath it, one where correlations exist without signals, and connection does not require contact. Physics learned to work with quantum entanglement, incorporating it into theories and technologies while accepting that it violated classical intuitions. The mathematical framework remained consistent even if the implications remained strange. This realization reshaped how reality is understood. Objects were no longer fully independent. Separation in space did not guarantee separation in behavior. The universe allowed coordination without communication, order without exchange. Quantum systems exhibited holistic properties that could not be reduced to the properties of their parts. The whole was genuinely more than the sum of its parts in ways that classical physics never anticipated. This did not enable faster-than-light messaging. It did not allow control at a distance. But it did force a redefinition of what it means to be connected. Reality was not stitched together locally. It was constrained globally. While entanglement could not transmit information faster than light, it created correlations that reflected global constraints on quantum states. The universe enforced consistency through mechanisms more subtle than causal signals. More deeply, it reshaped humility. Intuition had once again failed. The universe was not obligated to respect the stories humans preferred. It obeyed rules that were consistent, precise, and deeply non-intuitive. Nature operated according to mathematical principles that defied everyday experience and challenged philosophical assumptions about the nature of reality. Scientists learned to trust mathematics even when it led to conclusions that felt uncomfortable. Today, this insight underpins technologies that rely on correlation rather than control. It shapes how information is defined, It influences how security, computation, and measurement are approached. The prediction nobody wanted to test now quietly powers the future. Quantum cryptography exploits entanglement to create unbreakable codes. Quantum computing harnesses it to perform calculations impossible for classical machines. Quantum sensors use it to achieve measurement precision beyond classical limits. What was once a disturbing prediction became the foundation for transformative technologies. The experiment did not reveal a flaw in reality. It revealed a flaw in expectation. The universe was always capable of this behavior. We simply were not prepared to see it. Nature had always exhibited quantum entanglement. The strangeness was not in the universe, but in human assumptions about how it should operate. By testing the prediction nobody wanted to test, science discovered not that nature was broken, but that classical intuitions were incomplete guides to reality's deeper structure. Subscribe to join the journey. The prediction